Not all locks are created equally. No, you're not going to lock your house with that old padlock you used on your bike as a kid. Although that combination lock from high school might just work. Except that I would probably get locked out of my own house. I still have nightmares about that high school locker. Anyway, in our IoT designs, our locks are definitely not created equally. The same security plan you employed for that connected toaster you've been working on might not be the best idea for anything industrial IoT related. And what about medical designs? What if people's lives are on the line? What kind of lock do we use then? Hi, I'm Amelia Dalton, host of Chalk Talk. Connected medical devices require a unique set of security design requirements, including sterilization compatibility, use case specification, and performance degradation. And a software-only security solution with a non-secure MCU might not be the best way to go. Fortunately, Scott Jones from Maxim Integrated is here to set our mind at ease. In this episode of Chalk Talk, Scott and I discuss what secure authentication is all about, and Scott walks us through exactly how we can use the SHA-3 authentication model to get our medical security plan on track. And before we get started, don't forget to click that link. There you can find even more information about the Secure Authenticator IC from Maxim Integrated. Hi, Scott. Thank you so much for joining me.
Thank you. Thank you for having me.
Okay, so security is an important aspect of just about any IoT or embedded design today. And it goes without saying that this is especially important in the medical world. Now, Scott, what security factors are we talking about here? Now, I would imagine that counterfeit parts would come into play.
Yeah, you're right. I mean, in the medical world, if we think about the products that exist, we have, for example, tools, sensors, peripherals that are used in procedures, and we want to ensure that those products are genuine, they're not counterfeit, they don't have some issue that would potentially, damage or be a risk to patient safety.
So, Scott, what devices should we be the most concerned about?
If we look at the products that are in the market, there are some high volume devices that really are the ones that can be problematic in terms of some of these risks. So disposables, consumables are the terms that we typically use to describe these products. And, for example, we might have a pulse oximetry sensor. And these things are used quite often in hospital environments. Sometimes they're used one time, sometimes they're used multiple times. But anyway, they're high volume. And so they can be a target to someone who's trying to produce, an aftermarket counterfeit version of it. We could also think about surgical tools, which, similarly could be high volume, could be high value and targets to counterfeiters. Infusion pumps, these things have a lot of components in them that, again, are replaceable targets. Once again, catheter-based instruments, similarly, these devices can have problems in terms of non-authentic or reused products being introduced into the supply chain.
So what requirements exist for these devices from a use management perspective?
If we look at these tools, they're designed to be used under specific use conditions. In some cases, they're designed to be used for a limited duration. Could be hours, could be days after that period of time has expired. The performance of the tool can degrade and could be, a performance issue in terms of its use. Or it could be designed for a limited number of uses, 5 times, 10 times, whatnot. Same issue after that number of use count has expired, performance can degrade. Or it could be a tool that's designed for a single use. So there's a lot of these in the market as well. After that one-time use for either performance again or biological safety reasons, it needs to be discarded.
So would a hardware solution be something that these device manufacturers should be looking at?
That's, certainly our opinion. We think so. There are different ways to do it, and so we Maxim bring to market a hardware-based, solution designed specifically for these types of problems or these applications. There's other ways to do it. So a customer could take a microcontroller, for example, do some firmware development, put that micro with firmware that they develop into the product and perform these same functions as far as protection that I described. But the issue with that is These micros, unless it's a secure micro, they are very susceptible to reverse engineering. And there are companies that exist in the market today that their job, if you will, is to break the micros, extract firmware, reverse engineer it, and make that available to somebody who's trying to counterfeit that product.
Okay, Scott, I think I understand about the design complications that medical designs bring to the table. But what does our solution look like? Where do we go from here?
We have products that we call secure authenticators. And these devices, again, are designed specifically for these types of applications. And if we think about how they can be used in one of these tools or sensors, we can do things like, we'll call it IP or intellectual property protection or device authentication. These types of functions will enable a medical device manufacturer to test and ensure that a product that's attached to an instrument is in fact genuine. We can also enable feature settings. So we could have a tool that, for example, has different levels of functionality. And again, a medical device manufacturer wants to ensure that, either, let's just say we have low, mid, and high range functionality. They want to be able to set that in a secure sense and not have that change. Our products can do this. Use management. So we talked about, duration or number of times or single event use. Again, we can solve those in a very secure way with these products. If you think about data that could exist in a sensor and we want to deliver that data over to an instrument, perhaps it's like operating parameters for the sensor itself. We want to make sure that that data has good integrity, hasn't been modified either maliciously or accidentally. We can solve this as well. Those are some of the use cases. If we think about device features that exist in our products, number one, they're very easy to use. I guess I got to get that out there. They're not micros, so there's no firmware development down at the device level to make these things work. They've got a function set that's designed specifically for these applications, and so we've got some host instrument that just utilizes those functions. Crypto. So I haven't really talked a lot about crypto, but our products have some light set of cryptography that we integrate into them to enable all of this stuff. If we think about cryptography, there's two classes of algorithms, symmetric and asymmetric. So this is the top level. Underneath that, there's a lot of variation that exists. We're not going to go into that. But I guess the point here is that we actually enable, if you will, or provide both asymmetric as well as symmetric, with our products. And there's various reasons why a customer would choose one over the other. Bidirectional authentication is important. For example, we have a sensor that gets authenticated to a tool. That's one direction. We also want, in some cases, the tool to authenticate itself to the sensor. That's the other direction. Secure use counting, I talked about, maybe this can only be used 10 times. We can do that with these products. Secure data storage. Again, this can be operating parameters that are stored in a sensor. We want to make sure that that data cannot be modified, so it's secured. It may be secure general purpose I/O to turn something on, turn something off in a secure sense, with these devices.
Okay, this sounds great. Now, what kind of use cases are we really looking at here? How can it be used?
There's a few scenarios that exist. I've touched on these, I think, a little bit, but, for example, we want to authenticate the tool of the sensor, the peripheral to the host instrument before it's used. Perhaps we want to update data in the tool, securely update data in the tool. This could be use data, for example. It could be, an expiration value that gets written to a part that's in a tool. So we want to securely update that data. We could have operating parameters that exist, within the tool, again, in this device, authenticated reads of that to ensure that that data has good integrity, or securely count the number of tool uses, that we've mentioned before.
Okay, Scott, can you walk me through how this works?
So I mentioned previously we've got, these different classes of algorithms, symmetric as well as asymmetric. I'm going to focus on a symmetric example and specifically using the SHA-3 algorithm. So SHA-3 is the latest algorithm that's been put out by NIST, National Institute of Standards and Technology. And so let's talk about using that algorithm in this example. And so what I'm showing here is, the classic example of Alice and Bob in terms of talking about cryptography. I don't know why Alice and Bob always get picked on, but they do. So let's start off by saying, for this to work, Alice and Bob have to have the same key. So for symmetric crypto, they got to have the same key for this computation that we're going to talk about to work correctly. With both sides having the same key would work like this. Alice has a message she wants to get to Bob, and she wants to make sure that that message is delivered and hasn't been modified. So she'll take that message, process it through SHA-3 with her key, and the output from that is a data value we'll call a MAC, or a message authentication code. And this is just a computational output from SHA-3, again, with that key input. It's a fixed value, so we can have an arbitrarily sized message going in. We get a nice fixed value coming out we're going to call a MAC. So Alice is going to deliver her message and the MAC to Bob. Bob gets that message. Bob has the same key as Alice. Bob processes that message through SHA-3 with his key, which again is the same as Alice's. He gets a MAC output, He also received the MAC from Alice. So now he's got his MAC, he's got Alice's MAC, does a comparison on those two. If they match, he knows that that message that he received from Alice is in fact valid. If not, then there's a problem. So fundamentally, this is, kind of the basics of how we would use SHA-3 to authenticate, a message coming from one entity, to another. It could be a tool back to an instrument, obviously, for this discussion about medical.
IP protection is a huge issue in security in general. So, Scott, can this SHA-3 be used with that in mind as well?
Yeah, so this is a very typical one for tools and sensors. And so again, what we're trying to do, or we want to do, for this case, is authenticate the tool or the sensor before it's used by a medical instrument. And for this, we also mentioned, the bidirectional capability. So in this case, we're going from the tool to the host instrument in terms of authentication. Again, what we're going to do here is make sure that that tool or sensor is genuine before it's used by the instrument.
Okay, cool. So walk me through this step by step.
So it's a little bit of detail, so just bear with me. Let's start at a top level and look at some of the fundamental elements that are going to exist on both sides of this discussion. So we've got a medical tool or a sensor and a medical instrument. If we look at the tool piece, there's some fundamental components that need to exist. And these are all going to exist within an authentication IC. And again, we're talking about SHA-3 for this example. So within this authentication IC in a tool, we'll have data values, including a unique serial number. We also call it a unique ID or a ROM ID. There's a lot of different terms, but think of this as a unique serial number that can be read out of this authenticator. We'll also have some application data stored in memory. It could be, again, operating parameters for the tool. We'll have a unique secret. So we talked about the secrets that are necessary for SHA-3 to work. We're going to have a unique secret in each one of our authentication ICs, different for each part, and that's important. We're going to get to some more discussion on that coming up, but a unique secret and also the ability to do SHA-3 math. And we're going to output from that SHA-3 computation a value we're going to call an HMAC. We looked at MAC before. This is an HMAC. It's just a variation on the way we do the computation. All right, so that's on the tool piece. Over on the medical instrument side, we're going to have a lot of the same components. We're certainly going to have the ability to do SHA-3 math. We're going to have a system secret now. So we got a unique secret over in the tool. We're going to have a system secret over in the medical instrument, which is different than that unique secret in the tool, and that's important coming up. We also have the ability within the instrument to generate we'll call it a challenge. Think of this as a question. We're going to send a question over to the tool. The tool is going to answer our question. We want that question to be different every time. Otherwise, the answer is always going to be the same. So think of it as a random challenge as well, but that's a pretty fundamental piece for the instrument side to have. And we can do all of this with a SHA-3 coprocessor, or we can do it with a microcontroller. If we're going to do it with a micro, it's pretty important that we be able to securely protect this system secret that exists over on the instrument side. And there's obviously micros that can do this, but it's important to protect this data value. It's a data value that's very important that not, get out to the bad guys. So with those fundamental elements, let's take a look at, how we would handle this unique secret that exists over in our tool or a sensor. Again, as I said, we're going to have a unique value over there. And so the way that we're going to get that unique value computed and put into our part is fairly straightforward. We're going to do this one time in a secure environment. It could be at the customer's location. Maybe the customer in turn contracts this out to someone else. Maxim can also do this. But again, in a secure environment, what we're going to do is we're going to take this system secret that we talked about previously. We're going to get this unique serial number or this ROM ID out of this authenticator device that's in the tool. And again, as I said, this can be read out of the part openly in the clear, so there's nothing sensitive about it. But we're going to get that out of the part and also some compute data, as I describe it in this slide. Just think of this as some additional information that, we'll utilize, for the SHA-3 computation. It's really not too important for this conversation. But the important items are the system secret and the slave ROM ID. Those are all inputs into this SHA-3 engine. Output from that is going to be this data value. We're going to call a SHA-3 HMAC. That is now the system-produced unique secret that gets programmed to the authenticator that's in the tool. So again, we do this one time, get that data value, program it in the part, done. In an end application, now that we have our part configured properly, it's in a tool or a sensor, let's talk about what the next steps would be as far as a host medical instrument operating with our part that's in a tool. So we have this unique ROM ID, we have this unique secret and SHA-3 engine over on the tool side that we're going to perform some operations with. And the first thing that happens is our medical instrument is going to request from our device this ROM ID value. Again, this is something that can be read in the clear without any risk. That happens, our part will send that over to the instrument side. So now on the instrument side, it's got all the data values. Think about what we talked about previously. It now has all the data values it needs to compute the unique slave secret that exists over in the tool. It got the ROM ID. It knows the system secret. That's got to be over on the instrument side. It has this compute data that we talked about as well. So those three inputs are now used by the medical instrument to compute with a SHA-3 HMAC the unique slave secret value that's over in the tool. Once it's gone through this operation, now both sides have the same secret. We can go to the next step. So here, let's look at how we're going to authenticate this tool or the sensor to the medical instrument. Again, the first thing that'll happen is the instrument will request from the device the ROM ID. We'll send that over. We talked previously about the need for the instrument to generate a challenge, a random challenge. So we've got that ability. That challenge is generated and delivered over to our part. So now our part has all the components that it needs to compute, a SHA-3 HMAC that's going to go back. So it's got its unique ROM ID, its unique secret, this challenge that came over, does some SHA-3 HMAC math on it, computes an HMAC _S in this image here, slave value, sends that over to the medical instrument. The medical instrument side has all these same components securely, right? So none of this stuff, the secrets haven't been communicated throughout these transactions, which is very important. But, it knows the unique slave secret. It computed it. It knows the challenge. It generated it. It read the ROM ID from the part. So now the medical instrument will do the same math, compute its host side HMAC, compare it to what it received from the slave. If there's a match, it knows it's talking to a genuine slave, and we can move on.
So, Scott, I know that medical designs have special sterility requirements. How does that come into play here?
For sure, we want to make sure that our tools and our sensors and whatnot are sterile before they're used on us in kind of a medical procedure. But there's three, let's just call them techniques that are used in industry, common techniques that are used to sterilize products. One of them is autoclave. So here we have sterilization with heat, steam, and pressure up to 134 degrees C, 2 atmospheres. Durations, overall can be on the order of 20 minutes. And so the good news is these secure authenticators that we're talking about are compatible with that. But we need to ensure that the cumulative exposure at these elevated temperatures is constrained. And the reason for that is, we have non-volatile memory technologies in these devices. If it's floating gate E-squared memory, for example, with extended periods of high temperature can cause memory contents to ultimately go away, be disturbed. So we got to just make sure it's constrained, and it's never an issue, is the reality. Again, these durations are short, so cumulatively we don't have a problem. Ethylene oxide is another one. This is a gas, and we use heat as well to sterilize. Again, compatibility, not an issue, so no constraint with our products here. But I guess a point to talk about with ethylene oxide, in fact, the EPA has been cracking down on the use of ethylene oxide for sterilization here recently within the last year or so. And so industry is kind of scrambling a little bit on dealing with that. One way to deal with it, and companies are doing this today, is the use of radiation, gamma and or E-beam to sterilize. This is done at room temp with minutes of exposure or duration. This can be problematic for secure authentication. We got to make sure that the product, the IC, the secure authenticator, is specifically designed to be used in this environment, can actually tolerate exposure to gamma or E-beam. And so the good news is we have products that can do this.
All right. Well, this has been a lot to take in today. Scott, what do you think are your biggest takeaways from today's discussion?
One of the important ones is that performance, human safety, brand reputation of the company who's got one of these products, in the marketplace, and also the need for, use management and authentication of the tools, the sensors, or whatnot. This is kind of one of the key takeaways. We have these requirements that apply to these medical devices. Number two, sterilization, is required. So we want to make sure that we don't have infectious diseases being spread. And the IC solutions, therefore, that are used in these applications need to be compatible with the sterilization techniques that exist. And then finally, secure authentication ICs. And for sure, Maxim's secure authentication ICs are designed specifically to address all of these needs. So we have targeted crypto, protected memory, use counting, and contact-efficient interfaces, whether it's Maxim's one-wire interface or RFID or NFC. And again, we have sterilization compatibility with these products.
Great. So where should I go for more information about this?
We tried our best to collect, a lot of good information on our website. We have a specific location on our website that really addresses this specific topic, medical disposables, medical consumables. So yeah, check us out.
Excellent. Well, I'm going to click that link and go to a Mouser.com page for more information. Well, Scott, I think that's all I have time for today. Thank you so much for joining me yet again. And before we go, you didn't forget to click that link, did you? There you can find even more information about the Secure Authenticator IC from Maxim Integrated. For Chalk Talk, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. Can't miss it, it's right across the top. Or head on over to YouTube. Keyword EE Journal.